Hello, I'm Glenn Patterson, PhD candidate in watershed science at CSU and developer and instructor for water courses in CSU's Online Plus program. Before coming to CSU, I worked for 30 years as a hydrologist with the U.S. Geological Survey. It's hard to talk about 21st century water issues without mentioning climate change. So in this lecture, I would like to address the effects of climate change on water resources. Abundant evidence shows that the Earth has been warming by several degrees centigrade during the last few decades. It's highly likely that this trend is related to increasing concentrations of carbon dioxide and other greenhouse gases in the atmosphere. Computer models that simulate the Earth's climate tend to agree that the warming trend is likely to continue throughout the rest of this century. The models show less agreement about projected changes in precipitation, but they do tend to agree that some places, primarily the higher latitudes, will be getting wetter, and others, primarily the lower latitudes, will be getting drier. The models also tend to agree that there is likely to be more variability in precipitation. Both floods and droughts are likely to recur with greater frequency, duration, and intensity. How are these projected changes likely to affect the hydrologic cycle? Warmer temperatures are likely to speed up evaporation from water and land surfaces and speed up transpiration from plants. No matter what happens to precipitation, the increased evapotranspiration will tend to dry out the soil and leave less water available to flow to streams, as well as less water available to infiltrate into the ground and recharge aquifers. Warmer temperatures will also cause a shift in precipitation toward less snow and more rain, and will lead to earlier and more rapid melting of both the seasonal snowpack and glaciers that have persisted for many years. Melting glaciers might cause increased runoff in glacier-fed streams in the short run, but in the long run, as glaciers shrink, the meltwater flow will gradually diminish. Along the coasts, rising sea levels are likely to inundate more low-lying land. Impacts on water resources of the United States would vary. While the shift from snow to rain and to earlier snowmelt would be widespread, other effects would vary by region. In areas with increased precipitation, such as the Northeast and certain coastal areas, as illustrated on the right side of this diagram, we would expect more severe storms and more flooding. In the interior of the country, illustrated on the left side of the diagram, we would expect more droughts, less stream flow, and less groundwater recharge. Water quality is likely to be affected too, with warmer temperatures, muddier water from increased erosion and sedimentation, more pollutants from stormwater runoff from heavy rains, and in some places higher contaminant levels due to less stream flow available for diluting wastewater discharges. Considering the impacts of both climate change and population growth, we are likely to see significantly more severe water scarcity by the year 2025. According to Population Action International, based on the United Nations Medium Population Projections of 1998, more than 2.8 billion people in 48 countries will face water stress or scarcity conditions by the year 2025. Of these countries, 40 are in West Asia, North Africa, or Sub-Saharan Africa. Over the next 2 decades, population increases and growing demands, in addition to changing climate, are projected to push all the West Asian countries into water scarcity conditions. By 2050, the number of countries facing water stress or scarcity could rise to 54, with a combined population of 4 billion people, about 40% of the projected global population of 9.4 billion. Let's look at how these changes are expected to affect one of our geographic focus areas, the Colorado River Basin. In 2012, the U.S. Bureau of Reclamation completed a large study on the future of water supply and demand in this heavily allocated basin, and into places outside the basin, such as Denver and Southern California, that receive its exported water. On the water supply side of the study, the effects of climate change were a significant factor in the calculations. In the words of the report authors, quote, "It is widely known that the Colorado River, based on the inflows observed over the last century, is overallocated, and supply and demand imbalances are likely to occur in the future. Up to this point, this imbalance has been managed and demands have largely been met as a result of the considerable amount of reservoir storage capacity in the system, the fact that the upper basin states are still developing into their apportionments, meaning they haven't quite used all their allocated water yet, and efforts the basin states have made to reduce their demand for Colorado River water. Concerns regarding the reliability of the Colorado River system to meet future demands are even more apparent today. The basin states include some of the fastest growing urban and industrial areas in the United States. At the same time, the effects of climate change and variability on the basin water supply has been the focus of many scientific studies which project a decline in the future yield of the Colorado River. Increasing demand coupled with decreasing supplies will certainly exacerbate imbalances throughout the basin." Unquote. The results of the study are summarized in this graph, which covers the historical period 1919 to 2008 and the future period 2013 to 2060. Supply is defined in terms of the reconstructed natural flow of the Colorado River at Lee's Ferry, Arizona, which is commonly used as the dividing point between the upper and lower parts of the basin. Analysis of stream flow records has shown that 92% of the river's flow at Imperial Dam, the most downstream gauging station on the river in the U.S., is derived from tributaries upstream of Lee's Ferry. Natural flow refers to the flow that would have occurred in the absence of upstream diversions and reservoir operations. The blue line in the historical part of the graph represents the 10-year running average of natural flow at Lee's Ferry. You can see two sustained periods of relatively high flow in the early part of the 20th century and in the 1980s. You can also see three periods of sustained low flow in the 1930s, 1950s, and at the end of the 20th century. The central issue addressed by the report is illustrated by the convergence of the 10-year running average of demand, represented by the red line, with the 10-year running average of supply, represented by the blue line. Looking to the future, the report takes three basic approaches to estimating the future supply. Two of these three approaches are based on the assumption that the future will imitate the past. The first approach, illustrated in this slide, assumes that the average and the variability of future stream flows will be similar to flows during the observed period of record, which covers the 107-year period from 1906 to the present. The second approach assumes that the average and the variability of future stream flows will be similar to flows during a longer period as determined from reconstructions based on the width of tree rings. In the western U.S., tree rings have been found to be closely correlated with annual stream flows, with wet years producing wider tree rings. This reconstruction covers the 1,250-year period from the year 762 to the present, which includes some long periods of both above and below average flows. The third approach departs from the assumption that the future will imitate the past. This approach relies on global circulation models to simulate future climate. These models incorporate the effects of increasing concentrations of greenhouse gases in the atmosphere and the changes in climate that are likely to result. The models include various assumptions about the rates at which greenhouse gases will be added to or removed from the atmosphere. These assumptions are known as emissions scenarios. The global models can be regionally downscaled to provide greater detail about a particular region such as the Colorado River Basin, and they can be linked to hydrologic models to provide projections of future stream flow. There is very strong agreement among the 16 models that the Southwest will continue to warm during the next 6 decades. The warming is projected to occur during all 4 seasons, with the largest increases during the summer. The cross-hatching in the maps represents trends that are statistically significant. There is also good agreement among the models that the Southwest will experience decreasing precipitation during this period. The amount of the decrease depends on the emissions scenario, with higher emissions scenarios, or more greenhouse gases, producing greater decreases in precipitation. The result is that the projected future stream flow and hence future water supply based on the climate models, as represented in the right-hand part of this table, is lower than the projected future stream flow based on the approaches that do not incorporate the effects of climate change in the other 3 columns. The difference is on the order of 1 million acre-feet per year. The projections based on the climate models also exhibit a greater tendency toward extended droughts and less likelihood of extended water surpluses. The climate models, as indicated on the right-hand column of this table, project a 48% chance of 5 years or more in a row of water deficits, compared with 22 to 30% chances using the other approaches. The climate models project less than 1% chance of 5 years or more in a row of water surpluses, compared with 15 to 28% chances using the other approaches. Returning to the summary graph, we see that the blue trace for the future projection of supply is fuzzy, encompassing most of the range of variability of the observed record. That's because it incorporates all 3 approaches to estimating future supply. If we put more emphasis on the approach that incorporates the effects of climate change, the graph would look more like this, and the message about the future would be that by the year 2060, demand is likely to exceed supply by an average of about 3.2 million acre-feet per year. This gap between demand and supply is about the same volume as the water stored in Flaming Gorge Reservoir in Utah, the largest reservoir on the Green River, one of the main tributaries of the Colorado. So what is being done about this problem? The study evaluated a large number of possible actions that could be taken to reduce demand, augment supply, improve our knowledge of the system, or mitigate some aspects of the problem. By considering the advantages and disadvantages of each potential action, they narrowed the list down to 10 actions listed here that show promise for helping to resolve the problem. The Bureau of Reclamation and their partners are taking steps to get some of these actions underway. In summary, hydrologists and water managers are starting to adjust to the concept that the occurrence and behavior of our water resources in the future are likely to be different from the past. Changing climate is likely to bring warmer temperatures, more evaporation, earlier snowmelt, a shift from snow to rain, less infiltration, less soil moisture, less groundwater recharge, less stream flow, and more variability in precipitation and stream flow. More people in the world will be influenced by water scarcity, and more innovations will be needed to find ways to conserve water, enhance supplies, and more efficiently manage the resources we have. Thank you.